Continuing, we've got the definition of expected value. The expected value of a discrete random variable, denoted with a capital E, is synonymous with the mean, and it has the same formula. So we see E equals, and we see exactly the same formula for calculating the mean for a discrete random variable. What's up with this? Why would it have a second name? Why would we call it the mean sometimes, but other times we're going to call it the expected value? It's a very small nuance in just the way we interpret that number. Okay, so I wrote, besides thinking of this measure as the average data value, we can also think of it as the expected number of times a particular outcome will occur. Okay, let's go back to the World Series data, right? So we found the mean just a moment ago. I have to look back at it now. We found it to be 5.825, right, in number 2. So what is 5.825? Well, you could think of it as the average number of games in the World Series over those years, or you could think of it as the expected number of games in the next World Series. So if somebody said, hey, we've got all this data from the 40 years of World Series, so the World Series happening, later this year, how many games should we anticipate in the World Series? And, doing an average, makes sense. So you think, well, over 40 years, the average was 5.825. So, you know, we're going to bet that there will be 5.825 games in the next World Series. Okay, so maybe that sounds kind of ridiculous in this particular context, and you're right. So there's not going to be 5.825 games that they play. Like maybe they play 5 games, or maybe they play 6, but it's not going to be 5.825. It's not going to be a decimal, right? In other cases, that could totally make sense, that a decimal number could fit. There's more to expected value. So in some contexts, expected value fits really nicely. In other contexts, it's not going to be so useful. And even depends on who you are in relationship to what's going on. And we'll kind of get to that in practice number 3. Let's do it. Okay. It says a talk radio station has 4 phone lines to take calls from listeners. If the host is talking to someone, or it is a commercial, the callers are placed on hold. When all the lines are full, new listeners trying to call in get a busy signal. Okay, so there's this radio station at any given time. So maybe the host is just talking himself, or maybe he's talking to a caller. If either of those are happening, then anybody new calling in gets put on hold. And you actually want to be put on hold if you're calling a radio station, because that means you're in line, you're going to get to talk to the host. What you don't want is just a busy signal, because that means all their phone lines are full and you're not getting in line, right? So this particular station, they've got 4 phone lines. So one person could be talking, but then 4 other people could be on hold waiting. There you go. All right. So the probability that 0, 1, 2, 3, or 4 people are currently on hold is shown. So we've got this nifty little table here. And we've got all the values of our variable x and the probabilities that go with each of those. So we just kind of interpret that table. So, what's the probability that nobody is on hold at any given time? And it's only 0.10, or like 10%, that nobody is on hold. What's the chances we've got exactly 1 person on hold, right? 0.19. Okay, so you can see them all. 2 people on hold, 3 people on hold, 4 people on hold at any given time. And once they get to 4, well, they can't take any more. They don't have any more phone lines, right? So part A, find the expected value for the number of callers that are on hold. And we're kind of thinking at any given moment. How many people can we expect to be on hold at any given moment? Say, okay, well, we've got that same formula, right? So we'll go about it the same way. We'll take each x value, 0, 1, 2, 3, 4. We'll multiply them by their probabilities, and then we'll add them all up. So capital E, 0 times 0.10, plus 1 times 0.19, plus 2 times 0.36, plus 3 times 0.24, plus 4 times 0.11. Each x value times the probability of it occurring. I'd say just put that whole thing in a calculator, and there you go. 2.07. And I forget if I had to round that number or if it came out that way. I almost want to say I believe it just comes out to exactly 2.07. I don't think you have to round this one. Okay. And if you're wondering, all right, what are the units on that number? So I just have an idea of what that even means, 2.07. Okay, remember it's always the same as the x value, all right, which is the 0, 1, 2, 3, or 4. That's the number of callers on hold. So we would expect at any given moment for there to be 2.07 callers on hold. Now again, you look at that and you think, oh, come on, like there's never going to be 2.07 callers on hold. There could be 2 callers on hold, but not 2.07. Okay, so what's up with this? How is this useful? Okay, so don't think about it, from the perspective of like maybe the host of the station so much. Think of it as maybe put yourself in the position of maybe like the producer of the radio station or this particular show or something like that, or the manager of the whole thing. That leads us to part B. Why would it be useful to that person? Should the station consider getting more phone lines installed? Okay, so this expected value, very helpful. Do you think that the station should spend some money and have more phone lines installed? Would that be worthwhile? Would that make sense? I would argue here, no. And now there's not necessarily a right or a wrong so long as you got a good argument, but let me tell you why I would say no to this. Because they only expect 2.07 at any given moment. They've got 4 phone lines. And at any given moment, they're expecting something much closer to 2.07. So should we get a 5th or 6th phone line installed? Well, occasionally that's going to be helpful, but the majority of the time we're fine because we only expect at any given time for there to be 2.07, right? If this number was much higher, like if it was something close to 4, if it was like 3.8 or something, who knows? If it was really close to 4, then I'd say, yeah, maybe we get a 5th or even a 6th. But if it's down near 2, then I think the number of phone lines we have is sufficient. Okay, so you kind of got to think from a different angle about how that would be useful to someone, that number. Okay. Let's check out number 4. I love this problem. This is a classic expected value problem. It says 1,000 raffle tickets are sold at $1 each. Each ticket may win one of 4 prizes valued at $10, $50, $100, or $250. So they're going to give away these 4 prizes. And you think, okay, so they're selling tickets for $1, prizes. They're going to sell 1,000 raffle tickets. So your chances of winning one of the prizes is not so good. But, you got a shot. All right. What is your expected gain or loss if you purchase 1 ticket? Certainly somebody could purchase multiple tickets if they wanted to, but if you just bought 1 ticket, what's your expected gain or loss, right? This expected value problem. So here's what we're going to do. We're going to have to find probabilities and that, and there's more to it, of course, than number 3. Here's what we're going to say. This is a capital X, by the way. Don't get too hung up about capital X versus little x. Okay, so we're going to say capital X is the amount of money we gain. So in the problem, it says gain or lose for purchasing one ticket, but we need one way to think about this. And then it'll be clear what gaining and losing will be when we get to our answer. We're going to say capital X is just how much we gain, which would mean if we lose money, how are we going to think about that? As a negative. Okay, so if we lose money, we think of that as a negative gain. But we need just one way to consider it. All right. So we're going to make a table kind of similar to what we saw in number 3. We're going to list all the possible values of X, and then we're going to put their probabilities underneath. And then we're going to find the expected value. Okay. So here's what I've got. Let me talk through. I'm not revealing the probabilities of each, but these are the possible amounts that we gain. Now, you might be looking at those numbers and thinking, where did that come from? Okay, let's explain. So the first possible gain is $9. Okay, why $9? Okay, so this is the person that wins the $10 prize. But why isn't it 10? Oh yeah, because they had to buy a raffle ticket for $1. And I'm sure people are somewhat familiar with raffles if you've ever done one. They don't give you your money back. You're like, oh, here's your $1 back for your ticket that you bought an hour ago. No. They're keeping that $1. They'll just give you your prize and everybody's happy. Okay, so you win a $10 prize, but you lost that $1 when you bought your ticket. Okay, but you're not complaining, obviously. Okay, so then the 49, that's the winner of the $50 prize. So they win a $50 prize, but they had to spend $1 for the ticket. The 99 is for the $100 prize. The 249 is the $250 prize. Okay, well then what's up with this negative one on the end? Okay, so these are the 4 winners. But most people who go into this raffle, they don't win. Most people just lose their $1. Okay, and now they're probably happy with that because usually raffles are for charity. But yeah, most people gonna lose their $1. And 4 people win. Okay. Let's look at the probabilities that go with each of these possible outcomes. And I'll just show you everything here. So there's 1,000 people with tickets, and there's only 4 winners, right? So what are your chances of winning that $10 prize? 1 out of 1,000. Okay. What are your chances of winning that $50 prize? They're only giving 1 of these away, 1 out of 1,000. 1 person out of 1,000 wins the $100 prize. 1 person out of 1,000 the $250 prize. Well, how many people then just lose their $1? 996 people lose their $1. Okay, so odds are pretty good you're just going to lose your $1. It's almost a guarantee. You'd be shocked if you were a winner. But okay, it's for charity probably. Now, in this question, just be careful because in homework or other places like tests and things, here there was exactly 1 person that won each of these. But sometimes in raffles, maybe they give away like a few of these $10 prizes. Like, that could happen, right? So maybe like they have 5 $10 prize winners. Then we'd still put 9 here, but then it'd be 5 out of 1,000 if there were 5 $10 prizes, right? Okay, hopefully that makes sense. But here there's just 1 winner, 1 winner, 1 winner, 1 winner, 1 out of 1,000, 1 out of 1,000. Okay. And then to get the 996, just take 1,000 and subtract all of these ones. How many people don't win? Okay, let's go ahead and multiply these out, do our expected value. By the way, you could use decimals here if you wanted to. You don't have to use fractions. I think fractions are a little bit easier to work with in this situation, but you could certainly use the decimals. All right, let's calculate our expected value down here. So $9 prize times 1 out of 1,000. $49 prize, or excuse me, $49 gain, $9 gain, $49 gain, probability $249 gain. And then the negative, be sure to not add, right? We add because it's positive. If it's subtracted, then or if it's negative, we subtract -1 times 996 out of 1,000, multiply that all together, and you will get E equals negative $0.59. Okay. Remember, the units are the same as the X values. We could even say like dollars gained, if you really wanted to be even more specific. Wait a second. Negative gain. Okay, so go into this expecting to lose. And that's probably not new information, right? Of course, you expect to lose in this raffle or any raffle. But this number really gives us a better sense of how, of what's going on. Now, okay, so negative 0.59. Is that going to be helpful information for any one person who's playing this raffle? Hey, you can expect to lose 59 cents. No one's going to lose 59 cents. You're either going to win a prize or you're going to lose your dollar. Okay. Well, then who is that helpful for? It's helpful for the people who are running the raffle, because they're thinking every person that comes up and buys a raffle ticket, every time a raffle ticket is purchased, they just made 59 cents. So somebody else comes up, buys one, they're like, perfect. So, we sold it to them for $1, but then we're going to give away these prizes. And in the end, it's going to work out to be they just handed us 59 cents. Whether they win or lose, if they bought a raffle ticket, they just gave us 59 cents. Okay. And now you could kind of even go a bit beyond this, and I've got just a note here at the bottom. So if every person who walks up is giving this charity 59 cents and there's 1,000 people, you think, okay, so what's going on? Well, 59 cents times 1,000 people, the raffle company or whoever it is, they know they're going to make $590 by the time this is done. And they can even break it down into each individual purchase, if that's helpful for them to get out there and sell tickets. Hey, every ticket that's sold gets us 59 cents. Maybe that's motivating or something. Okay. We're going to stop this video right here.